Here we go again, another video, this one about percent yield. Okay, percent yield is referring to, okay, let's say you do a stoichiometry problem, okay, and you find out that you should make 10 grams of something, but then you do the reaction and you only get 8 grams of whatever, okay? So what you're going to do then is you're going to put the experimental value, the amount that you actually get, over the theoretical value, which is the amount that you calculate that you should get, and then you do 8 divided by 10 times 100, you would see that that particular reaction would be 80% efficient, okay? Or you would get 80% yield, okay? Now that's going to happen a lot in chemistry. You're going to do a T-chart, and you're going to calculate that you should get some certain amount of product, okay? However, you don't always get 100% yield, okay? Why? There's a lot of reasons why, okay? Just because. But just understand that that is the situation. Now, the experimental yield is always going to come from the lab, okay? That's always going to be something that you do in an experiment, okay? The theoretical yield is always going to come from a calculation or a T-chart, okay? Every time is going to come from a T-chart, okay? Let's do some problems. I know that I've got 32 grams of methane that's burned in a combustion reaction. So let's make that, that's 202 plus. So methane plus oxygen yields CO2 plus H2O. Okay, balanced already. So I'm starting off with 32 grams of methane. Now, it tells us in our problem that we have 30 grams of water that are actually produced. What do I do with that number? We're not going to do anything with that number yet, okay? This is the amount that's actually produced. So in the experiment, it's actually produced. We're going to save that one for later. What we need to calculate is the theoretical yield, which is going to be from our mole road. So we're going to do grams to moles, moles to moles, and moles to grams. So now, in order to figure out my amount of grams, of course, I am going to build a T-chart. Okay, so let's go ahead and build it. And so I've got 32 grams of CH4. And we're going to go from grams of CH4 to moles of CH4. From moles of CH4 to moles of H2O. And from moles of H2O to grams of H2O. Let's bring everything down. So now I know that I can relate moles to grams via the molar mass. 1 mole is 12.01 plus 4.04, 16.05. And mole to mole ratio is going to be where I have moles over moles. So 2 goes with this, 1 goes with this. And now I know that 1 mole of H2O is 18.02 grams. So theoretically, I should get, okay, I use that word theoretically because I'm calculating my theoretical yield. I should get, enter, divided by 16.05. I should get, oh, is that right? 32 times 2 times 18.02 divided by 16, yeah. I should get, my theoretical yield is 71.86 grams, okay? Now, this is where I'm going to go back and use my 30 grams, okay? 30 grams of water should have been produced, okay? So now that's going to be my, or actually was produced. So now that's going to be my actual yield. 71.86 is my theoretical yield. So I'm going to divide 30 divided by 71.86 and hit enter. I'm going to then multiply that by 100 to make it a percent. So this reaction was only 41.75% efficient. Okay, that's how you do percent yield. Okay, let's do one more of these problems just to make sure that you're awesome. And then that'll be it. Okay, so now this one says the reaction of combustion of an octane, blah, 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 74.3% efficient. Okay, so I know that 74.3 equals A over T times 100. Okay, how many grams of water would you actually expect to form? So I know that I'm trying to solve for A. If 90 grams of liquid octane are burned. So we actually still have to calculate our theoretical yield as well. So that's what we're going to do first. We're going to calculate our theoretical yield, and then we can plug that number in there and then solve for A. So I've got, let's see, we're dealing with octane, which is C8H20, no, C8H18 plus O2 yields CO2 plus H2O. Let me balance this real quick. Hold. There we go. It's balanced. Okay, so now I know I'm starting with 90 grams of liquid octane, and I want to find out how much water I could theoretically produce in grams. Okay, so we're going to go grams to moles, and moles to moles, and moles to grams. So now I'm going to build my T-chart, 90.00 grams of C8H18. And then we go to moles of C8H18. And then we go to moles of H2O. And then we go to grams of H2O. Bring everything down. And moles of H2O. So now, how do I relate these things? Well, 1 mole is 12.01 times 8, enter plus 18.18, 114.26 grams. My mole-to-mole ratio, moles of H2O is 18, moles of octane is 2, and then 1 mole is 18.02 grams. So now let's see how much we theoretically should produce. 90 times 18 times 18.02, enter, divided by, open parentheses, 114.26 times 2, close parentheses, enter, 127.75 is my theoretical value. Goes in for T. Okay, so now all I have to do is 74.3 equals A over 127.75 times 100. Okay, first I need to get rid of the times 100, so I'm going to divide both sides by 100. Cancel, cancel. So I get let's see here, 74.3 divided by 100. Yeah, that's what I thought. 0.743. Where are we at? There we are. 0.743 equals A over 127.75. Okay, you put that over 1 and cross multiply, so we get A equals 0.743 times 127.75. We get 94.92. Actually, sig figs, how about 94.9? Grams of H2O. Okay, so that, my friends, is how we do this kind of problem. We'll practice it in class, and have a great time.